Hello again, and welcome back. Today we're going to be talking about the multi-parameter probe. The probe that we use in our lab is made by Thermo Scientific. It's called an Orion. The kind of brand or whatever is a Star A329, and it's a meter that we use very frequently in water quality work. Really made our life a lot simpler in some ways, especially on the dissolved oxygen, which is one of the parameters that it reads. We used to have to do dissolved oxygen via something called titration, and it was mixing a bunch of chemicals and using a titrator so that we could figure out exactly when a color change happened, and then we could read how much of the titrate we used in order to figure out the dissolved oxygen. That was all doable, but it was also sort of a pain in the ass to do it. So eventually they came up with an electronic way to do that, and that's what this meter is partially for. So the multi-parameter, as the multi suggests, reads more than one parameter, and other than dissolved oxygen, it also reads pH, which is the acidity of the water. It reads conductivity, which is sort of like how easily electrons can pass through the water. It's kind of like how easily electricity is able to pass through water. And temperature is the fourth parameter. The use for this is in general water quality. It's usually something you're going to be coming up with over time. You're going to make a series of readings over maybe over a few weeks, a few months, and then really kind of record all that data and then do it the next year and then the next year. A lot of times it's just sort of that base level. It kind of helps you decide whether the water quality is getting better or worse. And if it's getting worse, you can sometimes just help determine what's causing it by what those readings are doing. So we talked last time about the fact that we weren't going to go into too much calibration, and so I'll continue that here. The pH, we'll just kind of verbally talk about how we calibrate it. This is the most complicated one, requires a lot of, hi Casey, a lot of solutions, and basically using different pH solutions and getting a lower level, an upper level, and a mid-level. So we usually use something like a pH 4, a pH 10, and a pH 7. Kind of gives you some variation in there to what you're trying to do is bracket whatever your readings in the field are going to be. So if you know that you're going to be out in an area where it's almost always a pH 7.8 or 8, for instance, then a lot of times you only need to calibrate it between 7 and the 10. You don't necessarily need to go and do the pH 4 also. If you're unsure about what to expect, then you just do all three. Not that big a deal. So the first thing to notice about the pH probe is that it has this little bottle here on the end of it. This is a solution that keeps the membrane on the tip of the pH that is actually kind of doing all the work in good shape. And there's a special solution that you use to put in here. This is not just water. It's a pH solution that's meant specifically to keep the probe in good shape. So pH probe should always be in this. If you open up a box and are using a probe and you just see it sitting out, it's probably ruined already. And if it's not totally ruined, it might not be very reliable. So always make sure you do this. Another really important thing is when you take the probe out of the bottle, you want to make sure to unscrew the cap of this just a little bit, or just take it all the way off. The reason is there's a pressure to build up, and especially important when you're putting the probe in. So this is what the probe looks like. There's that little bulb on the end of it. There is what we're trying to keep in good shape. These little flanges on the side are just there to protect that physically from getting beat up. There's also another little probe that acts as another part of the pH reading. So when you put this cap on, we always put this on first, like that. There's a little O-ring that goes with that. Put it into the bottle and then screw it down. Really important, because if there's pressure in here, and with that seal, it kind of keeps the pressure in there, and if you're forcing that in there, you can actually pop the little bulb that's on the end and ruin your pH meter. A couple $100 for each of these probes, so that's something to really consider. Okay. Part of being in the field and the hassle of this is you have to do something with this bottle. You know, here I've got a nice picnic table to put it on, but in the field it's always kind of a hassle, so you do want to keep the solution in here. If you can find a cap without a hole in the top to put on it to keep it while you're using the probe, I would encourage you to do so. Finding the exact cap is sometimes a hassle. I have a second one of these also that I have labeled as water. Normally you don't want to put you don't want to store the probe in water over an extended period of time, but you also don't want it to go dry. So one of the problems with a pH probe in the field is that you're going to multiple sites. So you take your pH reading at one site, and then if you put it back in the bottle, that is a very low pH of like 4 point something usually, and so I always feel like that's sort of contaminating or potentially contaminating my my reading at the next site. Even though you can kind of rinse it off and stuff, I always feel better just having it in water. There's several different kinds of water. You can just use stream water, which is usually what I'm using for here. There's also denatured water, deionized water, and distilled water. And especially deionized water is also bad on these probes, so you don't want to use deionized water. Distilled water is okay, you can use that, but usually just tap water is best if you're just doing it for a short-term thing like between sites. So just grab it out of the stream. Once again, unscrew the cap, slide it in, and then put it on tight so it doesn't leak. The pH is testing the acidity of the water. Normal pH, as you probably know, is a pH 7. Anything below above pH 6 or above about pH 8 is of some concern. There are actually specific regulations depending on the species, and generally they're looking for somewhere between pH 6 and 8. If it gets out much beyond that, then there's probably something going on that's causing that to happen. And I won't go kind of into that, but that's something to be aware of, is that if you're getting high readings, you kind of need to find the source. Okay, that's the pH probe, and for the moment I'm just gonna put that back in here. One way to do this is to just partially screw this on so it's not watertight, and then slide it in carefully and then tighten it. That way you don't lose that O-ring that kind of was loose there that time I showed you. If you're in the field and that drops in the stream or something, it can be an issue for you. Okay, so other things that are read by this probe are the conductivity meter. Once again, this is testing the conductivity of the water and how well electrons are able to move into the water. Some waters that are kind of more saline or more have more minerals in them in general are higher in conductivity, and this can vary the chemistry of the water. A high conductivity can favor certain chemical reactions and not favor others. So that's one of the reasons we read it. For me personally, this is probably one of the ones that I use the least as far as my water evaluation, water quality evaluation. But we always read it to kind of know what's going on. We're going to talk eventually about electroshock and using electrofishers in a stream to electroshock fish. And one of the considerations to when you're setting up your electroshock equipment is the conductivity of the water. If you're putting all this electricity in, and depending upon how well the water transmits that electricity can determine how much of a shock that the fish gets. If you don't have enough, it's not going to stun the fish enough to cause them to react. And if you have too much, you can possibly kill them. So you want to be able to say, at least within a range, kind of what the conductivity is in your particular area. So good idea to check that at least once before you do an electroshock. And the third parameter is temperature. It's read both by the dissolved oxygen meter and by the conductivity probe. So as long as you have one or the other of those in, you'll get a temperature reading, and that just reads temperature. We can also read it with our digital thermometer, which we used during our continuous temperature probe. But it's a lot of times when you're just out and about, it's easier to just take the temperature with your multi-parameter probe. Okay, this is the dissolved oxygen meter, RDO meter. It is a way of telling how much oxygen is in the water. Once again, that's a very important parameter, as you can probably guess. There are limits to just what your pH is, your dissolved oxygen, or DO, is supposed to be. The level that we like to see things is around 8, and as sort of a minimum. And anything below 5 is really serious. Anything below 3 is pretty much going to be fatal. So one of the things that we talked about in the continuous temperature probe was the regulations for coho being certain temperatures. It didn't want to get above 18 degrees centigrade, and likewise for the same regulations require the DO be at or above 8 milligrams per liter. For DO, there's a couple of different ways to measure it. It's the same measurement, but 2 different ways to read it. You can do milligrams per liter, which kind of is just a base level, or you can do percent saturation. Percent saturation is the total amount of oxygen that is able to be held by that body of water at the temperature that it is at that temperature. So if you stick it in and you have 100% oxygen, then you know that there's really nothing much more that you can do to raise the oxygen level. It's up as high as it can. So that may mean that if the DO levels are still too low, so it doesn't necessarily mean the oxygen is okay. You can still have too low, so you can have maybe a 6 milligrams per liter level, but at 100% saturation. So that just means that the oxygen is as high as that water temperature and other conditions can make it. So that means that you may need to figure out a way to, for instance, lower the temperature of the water in order to raise the dissolved oxygen levels. When it comes out of your case, the way it's stored, it's in this white kind of protective tube. And before you take this off, when you first get it out, you turn your meter on and check what the dissolved oxygen level is in the air. And when it's in this tube, it's moist in the tube because there's a little wet sponge right here in the end. You put a little bit of distilled water on that. Doesn't take much. You don't want it to be like drippy wet inside here. These are connected with this, it's only separated by this little sponge. So a couple, maybe 3 or 4 drops of water, a small squirt of water on here once every month or 2 is all you really need. It doesn't really go anywhere. That then causes the air inside this white chamber to become saturated with air, so it's at 100% saturation. So when you turn your meter on, you should be able to test that and see if it reads 100. So to turn it on, there's just a little power switch right down here. You just push that, and it'll give you a little opening screen that tells you, what it is and your model number and stuff. And okay, first screen that comes up with is pH. So there's that screen, and then you push the channel button right here. That changes to conductivity, which, since our probes are not in the water, you have 0 conductivity. And then the third time you push it is your DO level. So right now it says 8.8, and your doesn't really tell you that much of what the oxygen is right here. What we're really looking for on that particular screen, if we're doing the calibration kind of idea, is you just want to find out the percent saturation. So there's a switch right down here that is labeled mode. You push that once, twice, and up in the little corner here you'll see percent saturation, or percent sat. That's what that stands for. And as you can see, it says 100, so our probe is calibrated. If it's not 100, then there's a little thing right over here, the screen that says cal. So that's telling you to push this button. So you push that button, and it would go through and calibrate itself so that it's 100%. So if you're at 101, that's okay. 99, that's okay. Anything much beyond that, then I would go ahead and recalibrate it. So our probe looks like it's doing good. So after you've done that, then go ahead and go out to the field. You are keep this on until you're out in the field. When you get to your site, then go ahead and remove it. The DO probe has a little top part. You can see there's a little kind of dividing line right there. This top part comes off and is replaceable, and that part needs to be replaced once a year. And it's sort of a programmed death for this thing, where if it doesn't get replaced every exactly 365 days, it shuts the machine off, or it gets an error message that tells you to replace your DO cap, and it won't work until you do that. Since this is kind of vulnerable, it's this top space up here that I'm not going to touch, but the top is sending out a little bit of a light kind of beam kind of thing, and that's what's helping you read. We put this on to help protect the whole probe when we're in the field. It also has the advantage of weighing it down so that it pulls it down into the water. If you have it in the water without this cap, the whole thing just kind of floats up, kind of bobs around like this, and you really can't get an effective reading. Okay, so when we're in the field, we have to decide where to take the reading within the water body. So for a lake situation like we're at today, our standard is to do it at 1 meter. I talked to you earlier about the turbidity meter, and that one we also did at the same depth. So that's sort of our standard. It could be various, depends upon kind of what you're trying to find out. 1 meter is, like I explained in that video, just kind of a good standardized depth for a lake. But you also might want to know what the surface is doing, or maybe just off of the bottom. It just depends upon what you're trying to find out. So for the lake, then it's 1 meter. In a stream, we want to get it halfway through the water column, which is also similar to our turbidity meter reading we talked about earlier. We can also use our long arm sampler if we need to, and the probes can actually be set right down in here. Sometimes you have to do them one at a time because they're kind of big, but that's a possibility. Sorry, Casey. Cat's getting in the way here. But in general, you would just go out into a stream. You always stand downstream of where you're putting your probe in, because you don't want to stir up the muck or do anything else, because that can actually affect your DO readings and your pH and everything for that matter. So always position yourself downstream of your actual sampling area. Pull off your your tube. So remember, unscrew it, pull it out gently, twist it back and forth, and like I say, try to watch that O-ring that's inside there not get lost. So put that in. Be very careful with what you're doing with that. So we've got a cat right here that likes to climb around things. Hopefully she'll leave that alone. Okay, with the pH, it's important because it's been in that solution to get it rinsed off. So use what's called a squeezy bottle. Fancy name for a bottle that allows you to squeeze water out of it. Be sure to rinse the probe itself off well. The little bulb that we were talking about earlier, not wanting to break. So the whole probe kind of gets rinsed off. And do the same thing with your conductivity meter. The conductivity meter reads in between these two, so it's important that nothing happens to block that area. So rinse that off well, and you kind of do the same thing with the DO meter, although there's really nothing much that's been contaminating that. Okay, so we will then set the meter. We're going to use the channel button again. So we went from pH to conductivity to DO, and now I'm going to use the channel button to kind of scroll through the other options, and one of them, as you can see there, shows you all three at the same time. So that's the one I use. It's just easy to get your data all at one time. So we get that ready to go, and then we come over, and I want this at a 1 meter depth. So I've put this little red marker at the 1 meter level, so I don't have to measure it each time. So that just goes down, and I usually put something heavy on the cord so that it'll keep it at that exact level. Yeah, I gotta adjust it a little bit. And then we just want to leave that for about 5 minutes. It just takes time, just like temperature or anything else, just takes time to kind of acclimate the meters themselves to the water. So if you just stick it in and take a quick reading and jump out, you're liable to get kind of a off reading. So we will just kind of leave that. I guess for this particular thing, we'll just assume that 5 minutes has gone by. And you remove your probes. So at this point, your probes are kind of wet. They've well, actually, I got ahead of myself there. You have to actually take the readings first. So let me let this stabilize. You can see this right now. The screen is just kind of flashing. Yeah, I think you can probably see that. It says stabilize up at the top. And you want to wait until things stop flashing and kind of lock in. And that's the readings that you take. So right now that says ready. It'll actually say ready, like the one on the bottom there for the DO. That says 106, that's ready. So that's what we're looking for. And as soon as I pull these out of there, there's actually a way to lock this in so that it'll just hold those numbers. They just calibrated this at the ODEQ, Oregon Department of Environmental Quality Lab, last week, and so they changed it so that it's not holding steady. As soon as I pull these out, it will change. So in that particular case, you have to write down the information as soon as while the probes are still in the water, otherwise it goes away. So in this particular case, we've got a pH of 7.08, so that sounds right. We've got a conductivity of 62.61, and that's microsiemens per centimeter. Very odd sounding unit. And the bottom one says 108% saturation. If I scroll through here, there's the pH, there's the conductivity, there's my 106% saturation for my DO. And if I scroll that one more, I can see that it's milligrams per liter. So you always, for dissolved oxygen, you always write down your milligrams per liter reading and your percent saturation, because you can't really, they don't make sense without each other. So that's, you always want to make sure that. So we've got a reading of 10.42. That's really good oxygen. That's excellent for here in the lake. Being so high, that's actually really high. And our percent saturation was 106, 107%. So you may ask yourself, well, how can it be higher than that? And the reason is the oxygen in cooler water can be higher than in warmer water. And as the sun starts to warm the surface of the water, you get a point where the temperature that the water is at and the 100% saturation level of that temperature of water is now higher than the actual air that's in the water. Sorry, it's kind of hard to explain. Essentially, the water's warming up faster than the water has the ability to get rid of the oxygen. So you end up with more oxygen than that temperature of water can theoretically hold. So because of that, you'll sometimes get oxygen readings of above 100%. So it's not uncommon. In fact, especially in the morning when things are starting to kind of warm up, it's actually pretty common to see that if you've got a lot of oxygen in your water. So our pH was right about in the right area with the 7. The conductivity 62 is just kind of what the conductivity is. It's not, there's no like regulation that it has to be one way or the other. It just helps you to determine other factors like chemical reactions for benthic processes and stuff. And then we had our RDO reading. So now we can pull it out. So if I was going to another site right now, there's kind of one of two things. We can either put the tube back on the pH probe. We could get some water out like I talked about earlier and do it, or we can put it back in its solution. We could take this off and put the white tube back on. But it's better on the equipment and easier on you to actually just wrap this up in a wet towel. So oftentimes I'll have, actually rather than a rag, I'll oftentimes use an actual terry towel like you have in your bathroom. You could use a hand towel, it's a little smaller. I just dip that in the water and kind of just give it a little squeeze out so it's not running, getting your car all wet. And then I'll just usually only dip about maybe a third of the rag into the water, squeeze that out a little bit, wrap that wet section around the probes, and then wrap the dry towel sort of around the whole thing into a little bundle. I'll just then put the whole thing in the car. You get to your next site, you just unwrap the bundle and stick it right in the water because it's all ready to go. So that's sort of the usual way that when you're in the field that you go from site to site. At the end of the day, however, it's a different story. After you've done your last reading for the day, then you want to use your distilled water to rinse off your probes, all of them, and go ahead and remove your protective case on that. Just kind of shake it off, rinse this down, lay on the front of it, like that. And it's okay to kind of dry this off a little bit. I wouldn't touch the front of it, but you can kind of give it just a light shake, and then put your protective storage case back on it. Once again, you want to make sure the sponge is wet on the end, but like I say, that's something you only really have to check maybe every week or two. There goes the sheriff boat. That's it, I think. Once again, the parameter readings are just your typical kind of readings that you just want to know about any particular body of water that you're working on. It's nice to have a continuous reading. We talked about the advantages on the continuous temperature probe of being able to see what it's doing throughout a longer period of time, for every hour, for instance, in the continuous temperature readings. That way you can see what it's doing throughout the day and not just the one instant you happen to be there. Same thing applies with these two. It's nice to be able to see a continuous reading, but to deploy a data zone is kind of a big deal. It takes a lot of effort and energy to deploy it and to do those audit readings and to download the data and deal with all the data. So depending upon what you're kind of looking for, if you're just taking something like this and just kind of looking at it as a broad spectrum, then it works real well. One thing to help minimize your changes is to try to do the reading at the same time every day. So if you do, let's say your normal work thing is you're going to do this once every 2 weeks in whatever body of water you're talking about, the idea would be to always go out on Monday at 10 a.m. or something like that, so that you sort of try to minimize that possibility of having things fluctuating throughout the day. It's not perfect. As time goes along, the sun comes up earlier, like in the summertime, and so 10 o'clock can have more light, having been hitting it all day or all morning long, much more so in the middle of the summer than in the middle of the winter. So it's not perfect, but at least it's it helps you with that to some degree. Okay, that's it on the multi-parameter probe. Really important probe to know how to use, and most of you, if you get into any kind of watershed, water quality work, fish work, or whatever, will end up using one of these at some point in time. And being all electronic and stuff now, it's actually pretty simple to use, and hopefully you'll got enough from today's lab to be able to know what somebody's talking about. If you're in an interview or something and somebody's talking about their water quality parameters, you'll know that the pH, temperature, dissolved oxygen, and conductivity are some of the common ones that they use. Okay, until next time.